Binary search algorithm. Binary search is a fast searching algorithm that works only when the array is sorted. Instead of checking every element one by one, it repeatedly cuts the search range in half. Let us understand binary search with a real-world example. Suppose you are searching for the word money in a dictionary. You will not start from the first page and check every word, because the dictionary is sorted alphabetically. So what do we usually do? We open somewhere in the middle. If the words on that page come after the letter M, then the word money must be somewhere before that page. So we ignore the right side of the dictionary and search in the earlier pages. If the words on that page come before the letter M, then money must be somewhere after that page. So we ignore the left side of the dictionary and search in the later pages. This is the exact idea behind binary search. Now let us convert this into a technical problem. We are given a sorted array. We are also given the target value. Our task is to find the index of the target element. If the target is present, we return its index. If the target is not present, we return -1. For example, we have an array with elements 2, 5, 8, 12, 16, 23, 38, 56, 72, and 91. And the target we need to search is 23. What would be the answer? The answer is the index of the target element in the given array, which is 5. The easiest solution is linear search. In linear search, we start from the first element and compare each element with the target. If the array has n elements, then in the worst case, we may need n comparisons. For example, if the target is the last element, we check almost the whole array. If the target is not present, again, we may check all elements. So the time complexity of linear search is order of n, since we are making n comparisons for a given array of size n. Binary search improves this by using the fact that the array is sorted. Let us search for 23. At the beginning, the left pointer is 0 and the right pointer points to the last element in the array. Since the array is of size 10, last pointer is 10 minus 1, which is 9. Now calculate the middle pointer, which is the average of left and right pointers. So, middle is equal to the average of 0 and 9, which is 4.5. Integer value of 4, so the middle index is 4. The value at middle index 4 in the array is 16. Compare this 16 with the target value. 16 is smaller than the target value, 23. Because the array is sorted, all elements before 16 are also smaller than 23, so we ignore the left half of the search range. Now our new search range starts from the element after the middle index. The left pointer becomes middle plus 1, which is 5. The right pointer stays at 9. Now we calculate the middle of the new rangem, which is the average of 5 and 9. The middle becomes 7. The value at middle index 7 is 56. 56 is greater than the target, 23. So the target cannot be in the right half of the search range after 56. We move the right pointer to middle -1, so the right pointer becomes 6. Now the range is from index 5 to index 6. Middle pointer is the average of 5 and 6, which is 5.5, which is integer value 5. The value at middle index 5 is 23. Compare this value to the target 23. Our array element is equal to the given target. It's a match. So we return the index corresponding to the matched element, which is the middle index, which is 5. Now let us see an important edge case. What if the target is not present in the array? For example, let us search for 40. Binary search will keep reducing the search range. When the search range becomes empty, we stop and return -1. Once the left pointer becomes greater than the right pointer, it means there is no valid search range left. So the target is not present in the array. This is the loop condition we use in binary search. We continue while the left pointer is less than or equal to the right pointer. When this condition becomes false, the left pointer has crossed the right pointer, there is no search range, so we return -1. Here is the pseudocode. We define a binary search function that takes the sorted array and target as arguments. The variables left and right act as pointers that define the current search range. Initially, the search range is the whole array, so we set the left pointer to the starting element at index 0, and we set the right pointer to the last element in the array with index array size -1. We have to iterate in a loop as long as there is at least one element in the search range. That means the left pointer less than or equal to right pointer. Inside the loop, meaning for every iteration, calculate the middle index, which is the average of the left and right pointers. Now we compare the middle element with the target. There could be three scenarios. Scenario 1. The middle element is equal to the target. Scenario 2. The middle element is less than the target. Scenario 3. The middle element is greater than the target. If the first condition is true, then we have found the target. The answer is the middle index, so we return it. If the first condition is false and the second condition is true, then our target can only be present in the right half of the current search range. So we update the left pointer to middle plus 1 and continue our search. If both the first and second conditions are false, then the middle element must be greater than the target. In that case, our target can only be present in the left half of the current search range. So we update the right pointer to middle minus 1 and continue our search. When the target is not present in the given array, the loop may end without returning any index. In that case, after the loop, we return -1 to specify that the target is not present in the array. We can make two small improvements to this pseudocode. First, we can improve the way we calculate the middle pointer. Currently, we calculate middle as left plus right divided by 2. This gives us the average of left and right. But in real programming, if left and right are very large numbers, adding them first may cause integer overflow in some programming languages. So instead, we use a safer formula. Middle is equal to left plus right minus left divided by 2. This gives the same result, but it avoids adding two large index values directly. Second, we can simplify the third condition. When we compare the middle element with the target, there are only 3 possible cases. So, after checking the first 2 cases, the only remaining possibility is the third case. That means instead of writing else if for the third condition, we can simply write else. Now let us understand the time complexity. Suppose the array has n elements. In binary search, after the first comparison, we remove half the elements. So the search space becomes n by 2. After the second comparison, search space becomes n by 2 power 2. After the third comparison, search space becomes n by 2 power 3. In general, after k comparisons, the remaining search space is n divided by 2 to the power k. We stop when the search space becomes 1. At this point, n divided by 2 to the power k becomes 1. In these k steps, we made only k comparisons for all the n elements in the array. So the time complexity is order of k. N is equal to 2 to the power k. Taking log base 2 on both sides, k becomes log base 2 of n. So the time complexity of binary search is order of k, which is equal to order of log n. Let us compare this with linear search, whose time complexity is order of n. If there are 1 million elements, linear search may take around 1 million comparisons in the worst case. But binary search takes only about log base 2 of 1 million comparisons. Since 1 million is close to 2 to the power 20, binary search takes around 20 comparisons. So for searching a target in an array with 1 million elements, linear research can take time for 1 million comparisons, while binary search can take time for only 20 comparisons. Before using binary search, remember these important points. The array must be sorted. The loop condition should usually be left pointer less than or equal to right pointer. This means there is at least one element in the search range. Please note that we move to the element either before the middle or after the middle. Do not set the left pointer to middle and do not set the right pointer to middle. That can create an infinite loop in some cases. Also, in many programming languages, we prefer this formula. Middle is equal to left plus right minus left divided by 2. If you solve this, you get the same average formula. But since we do difference of right and left, and then add its half to the left, this avoids overflow when left pointer and right pointer index values are very large. This can prevent integer overflow in many programming languages where integer size is fixed. For most beginner examples, both formulas may work. But in interviews and real programming, the second formula is safer. Thank you for watching. If this video was helpful, please like it and subscribe to the Program Guru channel for more videos on data structures and algorithms.